In question 1, we are given the velocity vector for a particle p, and we are asked to find the speed of p at time t is 2 seconds. So I will start by substituting t is 2 into the velocity vector. So when t is 2, v is 3 times 2 squared times I minus 6 times 2 to the half j. This leads to 12I minus 6 root 2j. We have been asked to find the speed, so this is the magnitude of the velocity. So we simply say that the speed is the magnitude of the velocity. So it's going to be 12 squared plus minus 6 root 2 squared all square root. And this gives an answer of 6 root 6 meters per second. In B, we need to find an expression for the acceleration. We know that the acceleration is the rate of change of velocity with respect to time. So it's going to be dv dt. So we get the power down and we deduct 1 from the power with respect to t. This gives 6ti minus 3t to the minus a half j. That's meters per square second. Please note that you cannot give your answer in column form here. You need to give your answer in the I and J form as requested in the question. In C, we are given the position vector of P at t is 4 seconds, and we need to find the position vector of P at time t is 1. I will actually start by finding an expression for the displacement S. This will be found by integrating the velocity. So it's going to be the integral of 3t squared I minus 6t to the half j dt. This gives an answer of 3t cubed over 3I minus 6t to the 3 over 2 over 3 over 2j plus a constant vector, I will call it c. And therefore we've got that the displacement S is t cubed I minus 4t to the 3 over 2j plus c. I will be using the fact that when t is 4, we've got the position vector S to be I minus 4j, and therefore I minus 4j is equal to 4 cubed I minus 4 times 4 to the 3 over 2j plus c. This leads to I minus 4j is equal to 64I minus 32j plus c, which means that minus 63I plus 28j is equal to the constant vector c. So we can write that the displacement S is t cubed I minus 4t to the 3 over 2j minus 63I plus 28j. We need to find the position when t is 1, so we substitute when t is equal to 1. We get that S is 1 cubed I minus 4 times 1 to the 3 over 2j minus 63I plus 28j, and this gives an answer of minus 62I plus 24j meters. This is the position vector after 1 second. In question 2, we've got a rough plane inclined to the horizontal at an angle alpha with tan alpha being 3 over 4. We've got a small block B of mass 5 kilograms held in equilibrium by a horizontal force of magnitude x newtons, and we are modeling block B as a particle. We are told that the magnitude of the normal reaction of the plane on B is 68.6 newtons, and we need to work out the frictional force acting on B. So I will need to resolve the forces on my diagram to see exactly what's happening. So we've got the diagram here. I will start with the weight 5g pointing downwards. Obviously I will be resolving this perpendicular and parallel to the plane. So perpendicular is 5g cos alpha. Now parallel to the plane, it's gonna be 5g sine alpha, and I will also add the frictional force. I'm not really certain on the direction of the frictional force. I have been told that the particle B is held in equilibrium, so it could be on the point of going up or on the point of going down. Well, I will assume that the friction is pointing down the plane, so it's about to go up, and I will let the calculations show whether this was the right direction. So down the plane, we've got 5g sine alpha plus the frictional force F, which we're trying to find. We've got the normal reaction of 68.6 newtons pointing perpendicularly and up here. And then we've got the x newtons. Notice that the angle here is also alpha, and I will resolve the x newtons as x cos alpha and x sine alpha. So I've got a clear understanding of all the forces acting here. At the same time, I should consider the fact that tan alpha is 3/4, so I draw a triangle here. We've got 3/4 opposite over adjacent, and this means it's a 3-4-5 triangle. That makes sine alpha 3/5 and cos alpha 4/5. So I will start by considering the forces that are acting perpendicular to the plane. So we've got 68.6 is equal to 5g cos alpha plus x sine alpha. So these are the forces acting perpendicular to the plane. So we get that 68.6 is 5 times 9.8 times the cos of alpha, which is 4/5, plus x times sine of alpha, which is 3/5. This leads to 68.6 minus 5 times 9.8 times 4/5, and all of it divided by 3/5 to be x, and this gives a value for x, which is 49 newtons. Now that we have found x, we proceed by considering the forces acting along the plane. So it's the x cos alpha acting up the plane and the 5g sine alpha plus f acting down the plane. So we simply say that x cos alpha is equal to 5g sine alpha plus f. So 49, the value of x, times cos alpha, which is 4/5, is 5 times 9.8 times the sine of alpha, which is 3/5, plus f. So we get that 49 times 4/5 minus 5 times 9.8 times 3/5 is equal to f, and this leads to f being 9.8 newtons. Remember, we didn't know for sure the direction of the frictional force. We decided to put it pointing down the plane. It turned out to be positive, which means I was lucky enough to pick the right direction. If you have solved this question by assuming that F was acting up the plane, you would have found F to be minus 9.8. So this means that the direction is in the other way, so it's down the plane, as we have just found here. And all of this helps us answer the II part, which says state the direction of the frictional force. We just found that it was positive when we assumed it was pointing down the plane, so we simply say down the plane to get the mark. In part B, we are told that the horizontal force x newtons is removed and B moves down the plane. Additionally, the coefficient of friction is 0.5, and we need to work out the acceleration of B down the plane. So it makes sense to redraw the diagram, removing the force x, just to see exactly what's happening here. So this is my diagram here. I'm adding the weight 5g, which I will resolve perpendicularly as 5g cos alpha and along the plane as 5g sine alpha. We then have the reaction because of the contact of the particle with the plane, and since this is going down the plane, we've got a frictional force pointing up the plane, which has reached a maximum friction, which is mu r, and we've got acceleration down the plane. I will start by equating the perpendicular forces. So we have that r is 5g cos alpha, and this is 5 times 9.8 times 4 over 5. And I will also consider the forces acting along the plane. Since we've got acceleration down the plane, I will be doing forces down the plane minus forces up the plane is mass times acceleration. And therefore, we've got that 5g sine alpha minus mu r is equal to 5a. So 5 times 9.8 times 3 over 5 minus mu, which we have been given this to be 0.5, times r, which is 5 times 9.8 times 4 over 5 is equal to 5a. And therefore we get that 49 over 5 is 5a, which means that a is 49 over 25, which is 1.96 meters per square second. In question 3, we've got a particle of mass 4 kilograms being at rest at point A. We've got two forces, F1 and F2, acting here, and P moves in the direction of the vector 3, 1. We need to show that this means that lambda minus 3 mu plus 7 is 0. I will start by using the fact that the sum of the forces is mass times acceleration. So we've got that F1 plus F2 is equal mass, which is 4, times the acceleration, which is a. Now F1 is 4 minus 1, F2 is lambda mu, and this is equal to 4a. And therefore we end up with 4 plus lambda minus 1 plus mu is 4a. And I can get the 4 on the left hand side, a quarter of 4 plus lambda minus 1 plus mu is equal to a. Notice that the acceleration is constant. This means that we can use Suvad equations here, and therefore I could be using the fact that v is u plus at. We have that v is the initial velocity. It was at rest, so this is 0, 0, plus the acceleration, which is a quarter, times 4 plus lambda minus 1 plus mu times t, and this is equal to a quarter t 4 plus lambda minus 1 plus mu. We know that the direction stems out of the velocity, so in other words, we've got a quarter t 4 plus lambda minus 1 plus mu being parallel to the vector 3, 1, and therefore the ratio of the I and the j components must be the same. I could completely ignore the a quarter t and simply say that 4 plus lambda over minus 1 plus mu is equal to 3 over 1. I can cross multiply. 4 plus lambda is 3 times minus 1 plus mu, which leads to 4 plus lambda is negative 3 plus 3 mu, and therefore we end up with lambda minus 3 mu minus 7 is 0 as required. In part B, we are told that after 4 seconds P passes through the point B, and given that lambda is 2, we need to work out the length of AB. I will start from the fact that lambda is 2 and use this to find the value of mu. So if lambda is 2, substituting into the relationship we just obtained, we get that 2 minus 3 mu plus 7 is equal to 0, which means that 9 is equal to 3 mu, and therefore mu is 3. This means that the acceleration will be a quarter times 4 plus 2, 3 minus 1, which simplifies to 3 over 2, a half meters per square second. And I can proceed with the position vector being given by the initial position vector plus ut plus a half at squared. Now we are looking for the distance AB, the length AB, and I can set A to be my origin. So we were originally at A, and I can set A to be 0, 0. We're looking for the position vector when t is 4. So when t is 4, we simply say that the position vector is 0, 0. plus 0, 0 times 4 because the particle was initially at rest, plus a half times 3 over 2 times a half times 4 squared. So substituting all of this here gives me 12 4 meters. This is the vector AB, and all that is left to be done is for me to find the magnitude of this. So the magnitude of AB through Pythagoras would be 12 squared plus 4 squared square root, which gives an answer of 4 root 10 meters. In question 4, we've got a uniform rod AB having a mass of capital M and a length of 2a. We've got a particle of mass 2m attached at point C with AC being 1.5a. We've got the rod resting at A on rough horizontal ground, and it's held in equilibrium at an angle theta by a light string, and the string is perpendicular to the rod. We need to explain why the frictional force is acting horizontally to the right. Before answering this particular question, I would like to add all of the forces acting here. We start with the weight. It has a mass of m, so it's a weight of mg at a distance of a. This because the rod AB is uniform with a total length of 2a, so the center of mass is halfway through at a distance of a meters from point capital A. We also have got the particle of weight 2 mg at the distance of 1.5a from point A. We've got the tension in the string, and the tension is acting at a distance of 2a, the full length of AB. And then we've got the reaction at A, and we see that these three forces are acting perpendicularly to our line of sight, and the tension is the only one acting at an angle. So if I was to resolve this, there would be a component pointing to the left and a component pointing upwards. So for this to be in equilibrium, it means that this force here is acting to the right. So there must be a frictional force pointing to the right. And therefore we say that the only horizontal component is due to the tension in the string, which is acting to the left. And since the rod is held in equilibrium, the frictional force at A is acting horizontally to the right. We need to mention the word only to explain why there must be a component to the right, and therefore the frictional force at A is acting horizontally to the right. In part B, I need to show that the tension acting in the string, capital T, is 2mg cos theta. So I will start by revisiting my diagram with the forces added. We will be taking moments about A, and we've got clockwise moments due to capital Mg and 2mg. The capital Mg is acting at a perpendicular distance of A cos theta. So we have A cos theta times capital Mg, and the 2mg is acting at a perpendicular distance of 1.5A cos theta. So that's going to be 1.5A cos theta times 2 capital Mg. And this is equal to the anti-clockwise moment, which is 2A, the distance, times capital T, the tension, 2A capital T. Notice that there is an A term present throughout, so these will simplify out. And we get that the mg cos theta plus 3mg cos theta is equal to 2t. This leads to 4mg cos theta is equal to 2t, and therefore 2mg cos theta is equal to t as required. In part C, we are given that cos theta is 3 over 5, and we need to show that the magnitude of the vertical force exerted by the ground on the rod at A is 57 capital Mg over 25. This will be our capital R on the diagram here. So what I will be doing is that I will be resolving the tension into a vertical and horizontal component and proceeding by considering the vertical components. So resolving the tension here perpendicularly, the angle here is theta, so that's going to be T cos theta, and then to the left horizontally it's going to be T sine theta, and I could equate the vertical forces, the t cos theta plus r, with the mg and the 2mg, which means that we have t cos theta plus r is equal to mg plus 2mg. Now we will be replacing t with 2mg cos theta, which we found in part B. So we have that 2mg cos theta times cos theta plus r is equal to 3mg. We can now replace cos theta with 3 over 5. So 2mg times 3 over 5 times 3 over 5 plus r is equal to 3mg, which leads to 18mg over 25 plus r is equal to 3mg, and therefore r turns out to be 3mg minus 18mg over 25, which is equal to 57 capital Mg over 25 as required. In D, we are given that the rod is in a limiting equilibrium, and based on that we need to show that mu, the coefficient of friction between the rod and the ground, should be equal to 8 over 19. Now the fact that we are in limiting equilibrium simply means that the frictional force F is equal to mu r, and we have just found that r is 57 mg over 25. Now once more revisiting the diagram, we can see that the horizontal forces should be balancing out, so t sine theta should be equal to F, and therefore t, which was 2mg cos theta times sine theta, should be equal to mu times 57 mg over 25. It makes sense to draw a triangle here to figure out sine theta. We know that cos theta was 3 over 5, so this is 3 and this is 5. It's obviously a 3, 4, 5 triangle, so cos theta is 3 over 5 and sine theta is 4 over 5, and therefore we get that 2mg times 3 over 5 times 4 over 5 is equal to 57 mg over 25 times mu. Now 2 times 3 times 4 is 24, so we've got 24 mg over 25 is 57 mg mu over 25. The 25s cancel out, the mg's will also cancel out. At the moment we are standing at 24 is 57 mu, so 24 over 57 is the value of mu, and this simplifies to 8 over 19 as required. In question 5, it's a golf ball which is at rest at point A on horizontal ground. It is hit and initially moves at an angle alpha to the ground. The distance AB here is 120 meters, and we are modeling the ball as a particle moving freely under gravity with an initial speed of capital U meters per second. We need to show that U squared sine alpha cos alpha is 588. I will start by annotating my diagram here with U, the initial speed, and I will be resolving horizontally it's U cos alpha, and vertically it's gonna be U sine alpha. Now we'll be considering horizontal and vertical motion separately, so we've got that the initial speed in the horizontal direction ux is U cos alpha, and the acceleration in the horizontal is 0, whereas in the vertical we've got uy is U sine alpha, and the acceleration in the vertical is simply minus g. I will be using in the horizontal s is ut plus a half at squared. So I will be using the fact that we have a total range in the horizontal of 120 meters. So 120 is u cos alpha t, and the half at squared term is 0 because the acceleration is 0. Now vertically the displacement is 0 because the ball hits the ground after 120 meters, so vertically the displacement is simply 0. So we've got 0 is u sine alpha t plus a half times minus gt squared. I can factor out the t here, and I'm left with u sine alpha minus a half gt. This will help me get the time of flight because I see that the solutions are t is 0 or u sine alpha is a half gt. So 2u sine alpha is equal to gt, which means that 2u sine alpha over g is equal to t. Obviously, the solution of t0 corresponds to the initial time when the ball is on the ground, and t is 2u sine alpha over g is the time when the ball hits the ground again, so that's the time of flight. So I can use the expression for t and replace it here. We get that 120 is equal to u cos alpha times 2u sine alpha over g. We can simplify the 120 with the 2, leaving a 60 on the left hand side, and we can then proceed through cross multiplication. 60g is u squared sine alpha cos alpha. Well, 60g simply means 60 times 9.8 is equal to u squared sine alpha cos alpha, and 60 times 9.8 is 588, which is equal to u squared sine alpha cos alpha as required. In B, we are told that the ball reaches a maximum height of 10 meters above ground, and we need to show that u squared is 1960. So now we'll be using v squared is u squared plus 2as in the vertical component. So the moment we attain the maximum height, the component of the velocity in the vertical direction is 0. So 0 squared is u sine alpha, the component, the initial component of the velocity in the vertical direction, squared, plus 2 times minus g times 10. So 0 is u squared sine squared alpha minus 196, and therefore this leads to 196 is u squared sine squared alpha. Somehow I need to use the result from part A, so I will simply write this below. So 588 is equal to u squared sine alpha cos alpha, and divide both sides. So 196 over 588 is simply a third, and on the right hand side the u squared cancels out. The sine squared alpha with the sine alpha leaves me a sine alpha in the numerator and a cos alpha in the denominator, which is simply tan alpha. So we get that tan alpha is a third, and therefore I can now draw a triangle here. Tan alpha is a third, opposite over adjacent. I can use Pythagoras theorem to get the hypotenuse. It's 3 squared plus 1 squared square root, which is simply root 10. And therefore we see that sine alpha is 1 over root 10 and cos alpha is 3 over root 10. So we can simply say that 588, which we found to be u squared sine alpha cos alpha, is u squared 1 over root 10 times 3 over root 10. So we get that 588 is 3u squared over 10. So 5880 is 3u squared. And if I divide by 3, I get 1960 for u squared as required. We are then told that we've got a refinement of the model that will take into account the effect of air resistance. The motion of the ball is now modeled as that of a particle with an initial speed of capital V meters per second, and this refined model is used to calculate the value for V, and it says which is greater, capital U or V, giving a reason for your answer. Well, if we've got air resistance, then this will be opposing motion, and therefore to attain the 120 meters horizontally, we will need a greater initial speed. So we simply say that V must be greater since air resistance will oppose motion, and therefore a greater initial speed is needed to cover the 120 meters horizontally. In D, state one further refinement to the model that will make the model more realistic. Well, for this type of question, it's always good to go back to the assumptions of the model. We assume that the ball was a particle. We modeled the ball as a particle. And another thing we could focus on is the value for G. So maybe the simpler thing to say is that use a more accurate value for G. And the second thing to say that will also qualify for the mark would be to take into account the dimensions of the ball, because if you are modeling something as a particle, this simply means that you are ignoring the dimensions altogether.